Okay, so we're going to do the review here. So the exam scores for 14 students in the class are there. It's nice they put them in order. What is the percentile of the person who scores 85? Okay, so let's see. There are a total of 14 students and 14, 13, 12, 11. 14, 13, 12, 11. So this is the 11th student out of 14. So 11 divided by 14 is 78. Remember, we round down for percentile, so we're going to call it the 78th percentile. So an ecologist who was studying starfish populations collected starfish, the species Pisaster. He's interested in the distribution of sizes of the species of starfish. One measure of size is arm length. Below is a cumulative relative frequency graph of arm length in centimeters of 102 Pisaster individuals. What are the approximate values of the mean and the interquartile range? So let's go with the median, not mean. Median. If you scroll over and scroll down, it looks like about 15. So these guys are out. Okay, so now, and the other two, obviously it's 75, it looks to be 16. At 25, it looks to be 12. So this is a very tempting answer, I think, for students, but don't pick that one. Right, what is IQR? IQR is Q3 minus Q1. Well, it's a number. It's a single number. It's not two numbers. Those are bad answers, right? Just trying to trick you. 16 minus 12 is 4, so it's got to be that guy. Consider the following cumulative relative frequency graph of the scores of children who played the game at skee-ball at a birthday party. Player wins 3 tickets if they score between 50 and 70. So score between 50 and 70. What percentage who played skee-ball won 3 tickets? Okay, what percentage of children who played skee-ball? So I guess if you go up from 50, go over, to me looks like 20. Ooh, like, boy, this is a little bit of a guess, but looks like between 20 and 45. So 45% minus 20% is 25. That's the best I got there. I think that might be right. I'm guessing. Might need to check that one. Distribution of data set is normally distributed with a mean of 25 and a standard deviation of 8. Okay. Just going to draw it up here. So mean of 25, standard deviation of 8. If you calculate the standardized score for every observation, what would the mean and standard deviation of the results be? Standardized score. Okay, so standardized score, when it says this, that means Z. That's code for Z. So Z equals, what will the new mean be? Well, the old mean was this, so 25. Okay, so it's the value, which we're trying to convert a mean. So we're minus the mean of 25 over the standard deviation of 8. So I think that's 0 over 8, which is 0. Oh, well, if you think about it, it's got to be this, right? That's the only 0. Isn't 0 always the mean of for any z-scores, right? So 1 is always the standard deviation. That's true. So if you're standardizing, you're making the mean 0, and you're making the standard deviation 1. That's what a z-score is. Manager of a large company calculates the mean salary of all employees. The manager is considering giving each employee $3,000. So that's adding. How does it affect mean or standard deviation? The mean, which salary increased by 3,000, manager gives this bonus. How will the interquartile range change? But every value goes up by 3,000. So measures of center will change, right? These are going to change. They're going to go up by 3,000. Measures of variability or spread, these are going to stay the same, right? Everything is still the same amount apart. So the interquartile range is a measure of spread. It's not going to change. What's always the area under any curve? Not just a normal curve, but any curve. Skewed right, skewed left, always 1. That's true, 100%. So we know 1 is true. Okay, those are out. The mean is always equal to the median for any normal distribution. Mean, if it's approximately normal, they should be close. I guess if it's perfectly normal, it's perfect. So 2 seems correct, I think. So being picky about that. Interquartile range for any normal curve extends 1 standard deviation below the mean to 1. Now, like if you figured out like the z-score for 25%, so let's just do that. Menu 653. So if you wanted like, or let's do 75%, so Q3. That's 0.67 standard deviations above the mean. It's definitely not 1 standard deviation above the mean. So that doesn't seem true. So 3 is false. So it's not 3. It's got to be A. Heights of American men age 18 to 24, approximately normal. The mean of 68. I'm just going to kind of draw that. So mean of 68. Standard deviation 2.5. So I'm going to go to like, I guess 70.5 and then 73. And if I went one more, that would be, that's a 3 there. 5.5. So over 70.5. So all this is shaded, right? Well, this is 34% right there. 50% to the left of that. So that's 84%. So this must be 16%. The distribution of heights of a student in a large class is roughly normal. Moreover, the average height is 68 inches, approximately 95% of the heights between 62 and 74. So that does put 68 right in the middle. I like that. Okay, so 68 is in the middle. 6 below that is 62. 6 above that is 74. So those are equally spread there. So we know 95% of the data is within 2 standard deviations. So there must be one more standard deviation in between these. These are 6 apart, so that must be 3 apart. That must be 71. So I think the standard deviation is equal to 3. The proportion of scores in a standard normal are greater than 1.25 is close to what? So again, we're talking about normal curve, 0, standardized, so 1, 2, 3. This is z-scores, -1, -2, -3. 1.25, so somewhere in here and bigger, so that's 1.25. Well, let's get our calculator out. That looks like a norm CDF, right? Menu 652, 1.25. Big number like infinity. And it's these scores, so you leave the default there. 0.10565. That looks about right. The mean score on the AP Stats test was 68.5, standard deviation. The distribution scores was skewed to the left. Oh, so don't draw a normal curve here. So I do know the mean was 68.5. Standard deviation was 58. Ooh, okay. So how much of a difference is, let's see. So the mean was 68.5 and the score was that. So what's the difference between those two? So 68.5 minus 58. That's 10.5. So that's, well, so if I divide that by 15.4, which is the length of one standard deviation, so that's 0.68. So then you're kind of debating between one of these, right? Probably. Skewed to the left, so I just have to picture it. So 68.5 is the mean. The actual score was down here at 58. So that's below. So what was the z-score? It's got to be negative, right? So it's got to be that guy. Okay, pre-response. Scores of a reference population of the intelligence scale for children are approximately normally distributed with a mean of 100 and a standard deviation of 15. Okay, I'm just going to draw that. I think it's probably worth it here. So mean of 100, standard deviation of 15, 145. Sorry if it's a little messy. 85, 70, 55. What score will represent the 50th percentile? Well, so these are approximately normal. So, I mean, the median is the 50th percentile, right? And the median and the mean should be the same because it's approximately normal. So we think 100. The mean and median are equal. Sorry, because it's approximately normal. It's a metric there. A score in what range would represent the top 1% of scores? Okay, so this is a great use for, now you really want like this, there's something way over here, I don't know exactly how far over, that 1% is more than that, right? So a little bit more. But I really need to, for inverse norm, which is the command I need, 653, oops, sorry, menu, 653. 0.99 is the area under the curve because it always goes left with that command. And I do want to just go ahead and get the answer, so I'm just going to put in 100 for the mean rather than convert to z-scores, and then I think it was 15. So I believe that would be 1. So you want to show your work. Inverse norm. So the, let's see, area equals 0.99, comma, lower equals 100, comma, upper, I'm sorry, a mean standard deviation, I'm thinking of a different one. I think norm CDF, and that's 15. Sorry. But label them. You want to do that. And the answer, of course, this equals 134.895. Score in what range? So that value or bigger. So from 134.895 all the way up to, infinity or anything bigger than that would be the range that would represent the top 1% of scores. So what proportion of the reference has scores below 110? So I norm CDF that guy. So menu 652. Below 110, so 110, 100 standard deviation 15. And again, when you write out this command, you'd write, norm CDF, and you'd say lower equals negative infinity, upper, and so forth. I'm not going to write it all out, but you get the idea. And the answer there is 0.747. So what proportion? 74.7%. Scores between 80 and 110. Again, these don't hit there, so you're not going to use empirical rule, right? So we're going to norm CDF that bad boy. Menu 652 between 80 and 110, 115. And so you get the 0.656, I guess. Interquartile range for this guy. So kind of interesting. So we've got to find the IQR. So I think you'd use inverse norm, right? So menu 653, I want 0.25. And then menu 653, I want 0.75. So those are the two values for z-scores. Wait, why did I do z-scores? Let me get the actual numbers here. So I'm going to put mean as 100, 15. 100, 15. So it looks like 110. So what is the IQR? So it'd be Q3, which is 110 minus Q1, 20.2347. You would want to show that work. At least the 110 point whatever minus 89 point whatever equals that. Okay. Number 12, find the proportion of observations from a standard normal distribution that satisfies that. Okay, so that's not too bad. So again, it's just go to menu 652, 1.51, lower bound, upper bound, 0.84. Oh, what am I doing? Wait, what am I reading wrong here? Oh, there's a negative there. I was like, what is going on? That is crazy sauce. Okay. So negative one. I was like, I know there's something wrong here. It's like 1.51 is not smaller than 0.84. So the area under the curve there is 0.73 or 73.4%. What's z-score for normal distribution has 33% of the scores above it. Menu 65. We know the percent. Whoops. Menu 653. 33% of scores above it means I always go left, so 0.67. So point z equals 0.4399. Or by the way, you want to show that command with the inputs there when you do something like that. So norm CF and inverse norm, show the command. It's good to do. Comedy films have mean length of 100.9 and standard deviation of that. Drama films have a mean of 116, standard deviation of that. Paul Blart Mall Cop 2 has its length of 94, and The Lady in the Van has length of 104. Which film is shorter relative to the film's genre? Okay, so comedy film. So let's figure out this one. So comedy, we're going to do that one first. So Z equals 94 minus 100.9 all over 12.3. That's for comedy. And then Z for drama equals, that'd be 104 minus 116 over 15.9. So you're typing these guys in. So that one is negative 0.56-ish. And the other one? So negative 0.755-ish. Okay, which film is shorter? So mean length of 100.9. So the shorter is, the bigger the z, if you think about z-scores. So anything like this is 0, this is -1, anything for left is shorter. So this guy is shorter. This one's longer. Which film is shorter relative to this one? So the drama, because the z-score is smaller. Below is a cumulative relative frequency graph for the length of time a group of 62 students spend on no time limit final exam in Algebra 2. Sounds like fun. What are the values for the median and the interquartile range? Okay, draw lines. Draw lines is important. So it does look like it's right about there. So median looks like about 90-ish. Okay, so Q3 maybe is 115, not sure about that one. 113, maybe, it's hard to guess. Minus Q1, so minus Q1 is 25, so right about there-ish. That's 80-ish. Subtract those guys, get 35. I like, even it's nice just to include minutes, just little things like that. So the IQR, I should have my work up there, so I'm okay, it's 35 minutes. You want to see that little bit of work. We want to see that. The mean time students spend on the exam is 94.1 minutes, and the standard deviation is that. Suppose an exam proctor realized after compiling the data they had used the wrong start time. So each value for time on the exam needs to be reduced by 15 minutes. He also wants to express the time in hours rather than minutes. Man, this guy's getting crazy here. So find the mean of standard deviation. So let's see what's going to happen here. So first, we need to reduce the times by 15 minutes. So how is it going to affect the mean? How's it going to affect the standard deviation? So, I don't think the mean's going to change, right? So 94.1 minus 15. That's the new, so far, that's the mean, is 79.1. We're not done yet. Subtracting or adding, or subtracting, what is it going to change that? So right now, the standard deviation is 24.23. Okay, so then what happens? He also wants to express it in hours rather than minutes. So this is minutes. So to convert to hours, I think you divide by 60. So we're going to divide by 60 for this one and divide by 60 for this one. So both those should be affected by division, I think. So 79.1 divided by 60 and 24.223 divided by 60. 0.4038. Okay, so what did we just find? So that's the mean is, the new mean is 1.31 hours. And that's the new mean. And the new standard deviation is 0.403 hours. What are the values of the mean and standard deviation of the z-scores of the time spent on campus for all the students who took the exam? What are the values of the mean and standard deviation for the z-scores? Oh man, I mean, they like this question, I guess. 0, 1, 2, 3. I'm pretty sure that that's always the way the chart looks here for z-scores. So I think the mean is 0. I think the standard deviation is 1. That's always true. For any time you have z-scores and standardized scores, you got it. If you need to double check my work, because I didn't, then you would go through this and just see how I did. Hopefully that helps.